Hello everyone. What we'd like to do in this video is start talking about the inverse functions. Let's recall how trig functions work, and let's think about how to go backwards. That's really what an inverse function is. It's going backwards. So, recall we've been doing something like this. Let's say we have the function y equals sine of x. So what do we do here? Well, let's say what we wanted to do is, or what do we feed into sine? What does sine eat? Sine, the trig functions eat angles. You input an angle, and here you would get an output of a ratio. A ratio, basically, for a triangle, for sine, it would be opposite over hypotenuse. You get out some sort of ratio. If we're thinking about it on the unit circle, what we're plugging in is an angle, and what we're outputting is a height on the unit circle, however you want to think about it. So, for example, if we wanted to know what sine of pi over 6 is, you plug in pi over 6. Now let's figure out what the height on the unit circle would be. So we either could look at the unit circle or we could use our hand trick. Sine of pi over 6, put down our pi over 6 finger. Sine is the y coordinate, that would be root 1 over 2 or 1/2. You input an angle, you're outputting a height on the unit circle or a ratio of the opposite to the hypotenuse. But what we want to do is when we're doing an inverse function, remember how inverse functions work, is we're doing the opposite thing. So like what does a function do? It takes something from the domain and maps it to the range. So maybe you would plug in 3 and you get an output of 6. What is the inverse going to do? It's going to take the 6 and it's going to map you back to 3. It's the backwards function. So if I want to go backwards, let's say, I want to know what is a certain ratio, or in this case, what if I have a certain height on the unit circle, I would want to know what angle gets us there. That would be doing the inverse. Let's give a notation to what the inverse function would do. Okay, so if I wrote y is equal to sine inverse. So we do sine, we put a little -1 here. It's similar to when you have a function f of x, and you write its inverse like this. So we write sine, and we put a little -1 here. This denotes the inverse sine function. So this is the backwards function. And what was this function going to do here? So we're going to put an x here. Well, notice for sine, what does sine eat? Sine eats angles, and it spits out a height on the unit circle. What does sine inverse do? It does the opposite. It eats heights on the unit circle, or it eats a ratio. It eats a ratio of opposite to hypotenuse, and it's going to spit out an angle. It spits out an angle. Whenever you are thinking about trig functions, specifically the inverse trig functions spit out angles. Trig functions eat angles, they spit out ratios. Inverse functions eat ratios and spit out angles. So let's ask ourselves a question specifically about this inverse function. Let's try to give it an evaluation. For example, let's say that we would want to know the height on the unit circle when we had an angle, we want to know the angle if the height on the unit circle is, let's say, 1/2. We're asking ourselves the question, what angle gives us a height on the unit circle of 1/2? Well, let's take a look. Maybe we'll put it down. We'll put the outputs right here. What are we going to get an output of? Well, let's think here. Well, most certainly we saw a second ago that, an angle of pi over 6. An angle of pi over 6 gives us an output of 1/2. Is that the only one? I don't think so. Look at the unit circle. We'll give you 2 different ways to think about it. Looking at the unit circle, is this the only angle that gives us a height of 1/2? Nope. Over here we also have a height of 1/2. What is this angle? Well, this angle is going to be what? Pi, take away a pi over 6. This is 5 pi over 6. At 5 pi over 6, what are the coordinates? Well, we're going to have what? A -√3 over 2, and the height is 1/2. So pi over 6, but also 5 pi over 6. Is there only 2? No! What if I add 2 pi to pi over 6. I could just go around the circle again. So what's another one? I don't know. What's pi over 6 plus 2 pi? Let's write 2 pi as 12 pi over 6. 13 pi over 6. 13 pi over 6. And 5 pi over 6 plus 2 pi. 17 pi over 6. And then add another 2 pi, add another 2 pi, add another 2 pi. Or you could subtract 2 pi, subtract 2 pi, subtract 2 pi. There are an infinite number of angles that spit you out a height of 1/2. We could also see that on the graph of sine. Take a look, take a look. If I want to know what angle gives us an output of 1/2, well, look. This angle does it. This would be pi over 6. This angle here gives you an output of 1/2. That's what? 5 pi over 6. So on and so forth. This horizontal line is going to intersect this graph at an infinite number of locations. Why is this a problem? Because sine inverse is no longer a function if I write it like this. This is a problem. I want to have for a function, I want one input and one output. One input, one output. That's all I want. I don't want an infinite number of outputs. We want a function. We want a function. How do we fix this problem? Well, if we're going to be able to create an inverse function, and if we want to be able to use our calculators, I don't want to use an inverse button on my calculator and have it spit me out an infinite number of angles. I want the calculator, or I want the inverse function just to spit me out one possible angle. So how are we going to do this? How are we going to fix this problem so it only spits out one angle? Well, I have to make a choice on what possible angles it could spit out. So if I'm looking at this picture right here, I want to cut this function or make a domain restriction such that this horizontal line, which would represent a certain output, would only have one input to get me there. So I need to cut this function so it'll essentially pass this horizontal line test. Now there's many ways you could cut this. But the traditional way to cut this graph is to restrict it here. Now notice that if you give me any height on the unit circle, let's say 1/2, what angle should sine inverse spit out? It'll spit out just pi over 6. If you give me a height of -1, height of negative, I don't know, if you maybe give me a height of, I don't know, negative 1/3 or something like that, there would only be one angle to get you there. So if I make this restriction, sine inverse will now be a function. And that's what we're going to do. We're going to restrict to what function sine inverse is allowed to spit out. So let's draw it and talk about it. Okay. So when we're talking about the sine inverse function, so here we have y is equal to sine inverse of x. Remember what the inverse function does. It eats ratios. And it spits out angles. Okay? The only possible ratios you could spit in here, well, what are the possible outputs of sine? The possible outputs of sine are between 1 and -1. So the only numbers you could plug into sine inverse is something between 1 and -1. So we should take a note that. What would be the domain of this function? What would be the domain of sine inverse? Well, you can only plug in things between -1 and 1. So the domain would be all x, such that x is between -1 and 1. Okay, now I have to choose its range. I have to choose its range. What possible angles is it going to allow me to spit out? Well, I've restricted it. I've restricted it so it's actually only going to spit me out angles between -pi/2 and pi/2. Between -pi/2 and pi/2. It'll only spit me out angles between -pi/2 and pi/2. Now, I guess we could have made different choices of cuts for this function. I could have said, oh, it only spits us out angles between, how about 0 and pi/2? And then we kind of have to have a little gap, and then between pi and 3 pi over 2, but then the graph wouldn't be continuous. It makes it work a lot nicer if I make the cut here so that the inverse, which I'll graph here in a second, will be a continuous function. By continuous, I mean you could draw it without picking up your pencil. So this is how sine inverse works. Let's graph sine inverse. So what does the graph of sine inverse work? So I'm putting a domain restriction on sine. So we only have this piece of it. Okay, so we made this restriction. Okay, let's label these points right here. This is the point pi over 2 and 1. This is the point negative pi over 2 and negative 1. Now let's sketch its inverse. Let's sketch the inverse. What would sine inverse look like? So here we'll graph sine inverse. Sine inverse of x. Well, recall how inverses work. Remember, since an inverse maps me from my range to my domain, the x and y values switch. So if 0, 0 is on sine of x, then also 0, 0 will be on sine inverse of x. So 0, 0 will still be here. Okay, well, since pi over 2 and 1 is on sine, then 1 and pi over 2, so 1 and pi over 2, 1 and pi over 2 will be on sine inverse. And negative 1, since negative pi over 2 and negative 1 is on sine, then negative 1, then negative 1 and negative pi over 2 is on sine inverse. So here's negative pi over 2. And what sine inverse looks like, think about reflecting this graph over the line y equals x. It's going to look something like this. This is what the graph of sine inverse looks like. Has a restriction. Maybe I get a better red marker. This is what it looks like. So you tell me an output on the unit circle at a height, it could be 1 between negative 1. Now it's only going to spit you out one possible angle, and the angle will be between negative pi over 2 and pi over 2. A lot of this will really, hopefully sink in once we start doing more examples. But what I really want to do in this video is just give you a picture of all the different trig functions, or the inverse trig functions. Okay, just as a quick note here, so this is sine inverse. This is the graph of sine inverse. What does sine inverse do? That's really the key piece. You plug in a ratio, it's going to output you an angle, but the way sine inverse is programmed is it's only going to spit you out an angle between negative pi over 2 and pi over 2. That's the key thing to hold on to. Okay. So, I guess a quick comment here. We sometimes write sine inverse like this, but it also has a different name, sine inverse. Sometimes I see students get confused about this negative 1, because usually when you think about x to the negative 1, that's 1 over x. Okay, do not get confused here. This notation here does not mean 1 over sine of x. These are not the same. Well, why are they not the same? Well, we already have a notation for 1 over sine. Remember, 1 over sine is the same thing as cosecant of x. So don't get these confused. Sine, this just means sine inverse. This does not mean 1 over sine. This does not mean 1 over sine. So be careful with that. Another way to write a sine inverse is they might say sine inverse, but they also might say arc sine. Arc sine. Arc sine is another way to write that. Okay, just need to plug in my computer. It's about ready to die. Okay. So sine inverse, another way to talk about the inverse sine function is something that would be called arc sine. Let's do cosine. Okay. What would the graph of cosine inverse work? Okay, so let's say we have y is equal to the cosine of x. Okay, remember how cosine works. Cosine eats angles. and it spits out a ratio. It spits out a ratio, specifically the adjacent over hypotenuse on the for a right triangle. Or you could think that it spits out the width on the unit circle. But I want to go backwards. So I want to talk about the inverse cosine. Cosine inverse. This might be also called arc cosine is another way to write it. Okay, so think about what this function does. This function, cosine, it eats ratios. And it spits out an angle. And again, the problem is if I give you a certain width on the unit circle, there are going to be an infinite number of angles that give you that width. So what we want to do is we want to restrict the domain of cosine so that cosine inverse only spits you out one possible angle. So let's take a look at the graph and think about how we should cut it. 2 pi, pi over 2, 3 pi over 2. Let's do negative 2 pi, negative pi, negative pi. Oh, this is negative pi over 2, negative 3 pi over 2. 1, negative 1. Okay, so here's the graph of cosine of x. Okay. Now the problem is if you give me a certain width on the unit circle, and I want to know what angle gives me that width, well, there are an infinite number of ones that work. So what we want to think here is how should we cut this to make sure I'm only going to get out one possible angle. So I want to find a nice section of this that is basically going to pass the horizontal line test. A great way to cut this is actually between 0 and pi. And we want to cut it. We want to cut it so when we do its inverse will be a continuous function. There's plenty of ways you could cut this to make it pass the horizontal line test, but we want to cut it in a way so that the function is continuous. So we're going to make a domain restriction, and we're only going to be thinking about cosine between 0 and pi. This piece here, you can plug anything between negative 1 and 1, and now you're only going to get one angle that pops out. So now, when I think about the cosine inverse function, it will now be a function, and it will only spit me out angles between 0 and pi. Okay, so let's graph this. Let's graph this. Okay, so what are we doing? What are we doing with cosine inverse? Let's write its domain and range down. Okay, the domain of cosine inverse. Well, you can plug in ratios. Well, the outputs of cosine can only be between 1 and negative 1. So cosine inverse can only eat values. Between negative 1 and 1. Okay, and what is it going to spit out? What are we programming it to spit out? We don't want it to spit out an infinite number of angles. We're going to have it only spit out angles between 0 and pi. Between 0 and pi. So this is how the cosine inverse function works. Okay, and then let's just do a quick sketch of it. Let's do a quick sketch. Maybe we'll do it up here. Okay, so let's kind of grab these nice numbers here. So this is the point 0 and 1. This is the point, this here is the point what? Pi over 2 and 0. And let's grab this point right here. This is the point pi and negative 1. So if I want to know what the graph of cosine inverse looks like, okay, well, since 0, 1 is on cosine inverse, 1, 0 will be, since 0, 1 is on cosine, 1, 0 will be on cosine inverse. So here's the point 1, 0. Okay? Then the point 0 and pi over 2, so pi over 2 and 0 is on cosine, so 0 and pi over 2, 0 and pi over 2, 0 and pi over 2 is on cosine inverse. And since pi and negative 1 is on cosine, negative 1 and pi will be on cosine inverse. So here's negative 1 and pi. Okay, so this graph is going to look like, it's going to look like this. So here's the graph. Of cosine inverse. Notice here, what are you inputting into cosine inverse? You're inputting a ratio between negative 1 and 1. Remember, cosine only spits out things between negative 1 and 1. You plug something in between negative 1 and 1, and now it's only going to spit you out one possible angle, and it'll give you an angle between 0 and pi. That's how cosine inverse works. Okay, let's do one more. Let's do tan inverse, or arctan. The main things that we really need to remember from this lecture is what angles these inverse trig functions spit out. We'll be doing tons of examples of this in the next video. Okay, last one. Let's do tangent. Tangent of x. Let's go ahead and graph tangent really quick. Again, the way I always think about graphing tangent is, I usually think about the slope on the tangent line. Slope is 0, then as we get closer to pi over 2, the slope is getting bigger. Wow. And we can continue on. Okay. So what tangent is doing is tangent eats an angle and spits out a ratio on the unit circle. Tangent eats an angle. It eats angles. It spits out a ratio. The ratio of opposite to adjacent. But now I want to talk about the inverse tan function. So we want to talk about y, which is equal to tan inverse of x. This is also sometimes written as arctan of x. I oftentimes like using arctan instead to alleviate that confusion that this means 1 over tangent, which it does not mean 1 over tangent. Okay. So what does tan inverse do? It eats ratios. It eats ratios and it spits out an angle. Okay. So now the problem is if I pick a certain ratio or a certain output of tangent here, I want to know what input got us there. Well, notice the problem is for this output, this input gets us there and this input gets us there. So I want to cut tangent in a way that it only will spit me out one angle. And we want to cut this so it passes a horizontal line test and also so it's continuous. And the best way to do that is to take this sweet looking cubic piece here. This is where we want to make our cut. This is where we want to make our cut. Okay, so let's go ahead and I guess let's write down where does the domain and range of tan inverse? Okay. So what is its domain? What is its domain? Well, what are the possible outputs of tangent? The possible outputs of tangent, we'll think about it's a slope. It's a slope on the line. I could get a slope of 0. I can get a slope of 1. I can get any slope I'd like. I can get like an infinite slope. I can get super negative slopes. I can plug in anything I want into tan inverse. So this will be all x such that x is between negative infinity, and infinity. And what does tan inverse spit out? What is its range? Well, I've restricted it that it's only going to spit us out angles between negative pi over 2 and pi over 2. So y between negative pi over 2 and pi over 2. Notice that I'm not including negative pi over 2 and pi over 2. Well, because tangent is undefined at pi over 2 and at negative pi over 2. So this is the domain and range of tan inverse. The key thing to remember is when you're working with tan inverse, it's going to spit you out angles between negative pi over 2 and pi over 2. That's just how it's been created. I mean, what we could have done, and mathematicians could have done, is they could have made a different domain restriction. They could have had the restriction between 0 and pi. This section here would still pass the horizontal line test. The only problem is now the function, tan inverse wouldn't be continuous, and we usually like continuous functions. Again, continuous means I'd like to have a graph where I can draw it without picking up my pencil. Okay, so let's go ahead and graph tan inverse. Let's graph tan inverse. Okay, I need more board space. We'll erase this piece here. So if we want to graph tan inverse, here's pi over 2, here's negative pi over 2. That's our range. You can input anything you want into here from negative infinity to infinity. Well, these used to be horizontal asymptotes, and remember with inverse functions, the reflections over the line y equals x, so those vertical asymptotes of tangent become horizontal asymptotes of tan inverse. It's going to look like this. So here is the graph of tan inverse. Tan inverse of x. Here is its graph. This is an important graph to remember. This is probably one of the first graphs you've seen that actually have two horizontal asymptotes rather than one horizontal asymptote. Last quarter, if you took 141 here, when you're graphing rational functions, they always just had one horizontal asymptote. Tan inverse function is probably the first example function you've seen that has two horizontal asymptotes. Okay. Before we start doing examples, I just want to quickly recap what is the most important thing to remember about this lecture. Okay, it's good to know these graphs. It's specifically really good to know the graph of tan inverse. This graph pops up in calculus quite often. But this is the key thing to know. So I guess notes, key notes. Sine inverse, cosine inverse, tan inverse, spit out angles. They spit out angles. That's what they do. You plug in a ratio, you get an output of an angle. That's what they do. Okay, specifically what angles? Okay, sine inverse of x. It's going to spit out angles. Sine inverse spits out angles between negative pi over 2 and pi over 2. It's going to spit out angles here. Cosine inverse. This spits out angles. Cosine inverse, the way it's programmed, and you can test this with your calculator, it spits out angles between 0 and pi. Tan inverse. Tan inverse of x. Tan inverse of x spits out angles between negative pi over 2 and pi over 2. These are the key things to remember from this lecture. Inverse functions spit out angles. Sine inverse spits out angles in quadrant 1 and between negative pi over 2 and pi over 2. Cosine inverse spits out angles between 0 and pi. Tan inverse spits out angles between negative pi over 2 and pi over 2. We made these restrictions to make sure that these functions were continuous and also just to the functions. Okay. What we're going to do in the next video is we're going to get practice with evaluating these functions. We'll see you there. Take care.